Ian Mackish from La Trobe University, and he will talk about the research for higher order symmetry in quantum mechanics. So, Ian, please.
Okay, so thanks for the opportunity to speak. So the talk would be in two, let's say, aspect. One is if you want to, let's say, extend the search for symmetries to higher order one, and actually higher order one mean greater than two. So, and there's a reason for that. It's because when you look at order 3 and beyond, the compatibility equation contain h bar term in the higher derivative. So then there is no longer correspondence between the classical and quantum. So this search will be done with differential operators, and then I will connect with work by Painlevé, Chazy, Bureau, and more recently Cosgrove, and how in some way we are familiar with interactions that are rational or trigonometric or hyperbolic or even elliptic, but the general, let's say, feature of superintegrable system is to be connected with higher transcendental function. And then what I would do is to go on another aspect, which is forgetting about differential operators and any realization and show that you can work in the enveloping algebra of Lie algebras. So in some way, those approach are complementary. Maybe they intersect, but not completely. Okay, so this is loosely speaking based on some more, let's say, recent work on the topic. I might point out some older one. So the idea is to make, let's say, a complete characterization of classification of superintegrable system in different contexts based on Chazy equation. So this is the first to work, and in those work with Sarah Pause from Hawaii, this connect also with Painlevé 6. Okay, but let me explain the context. So we are looking at Schrödinger equation. We are in, let's say, many dimension. This can be on curve space. So this would be a Laplace-Beltrami operator in quantum mechanics. And very often this potential interaction, so the V of x, will be seen as a polynomial, a rational, or even trigonometric function. I want to highlight a special one, which is known since quanta quite a long time, which is when this potential is elliptic. It can be Jacobi or Weierstrass. And this case have been pointed out to be connected with Calogero elliptic model, generalized Lamy operator. They are relevant for semiconductor, band and finite gap system, position mass dependent. So a lot of work has been done on the elliptic case by various people. And this is the form of the equation below. You can see it looks simple because this is a one dimension ODE. Uh, and then there's this elliptic, so this is Jacobi elliptic function. But still, mathematician has spent quite a lot of time. This can be seen in some older textbook, for example, book by Whittaker. So this could be relevant for PhD students to look at those older reference. But this elliptic function is defined via a nonlinear equation. So this is, let's say, our best prototype of a Schrödinger equation where the potential depend on a transcendental function. So something that is defined via nonlinear equation. And in general, I will speak about exotic potential, and I will mention potential that depend on Painlevé transcendent. Okay, so those would be quite different than most of the system we encounter in the literature, and usually they're free limit or their limit to the classical system will only be trivial. Okay, so in that sense, they are purely quantum system. So just to go back on those Painlevé, they appear in the classification of nonlinear equation at the beginning of, let's say, 20th century. This is by Painlevé, Fouch, Gambier. There was 50 equation for which movable singularity are only pole, and then by process of exhaustion, only six of them were understood to be irreducible, but that was only proven in the 80s. So for quite a long time, the status of those six ODEs was not completely understood, but this is the complete classification. Here, pain level 1 up to pain level 6, they depend on some parameters. So for example, pain level 2 depend on parameter alpha, pain level 4 depend on two parameter alpha and beta, up to pain level 6, which depends on four parameter. And those parameters play an important role because for selected choice of parameter, there would be, let's say, infinitely many special solutions, and they can take rational form or hypergeometric. So in some way, those PLV, they admit very special points for their parameter, and they play a role also in quantum mechanics. Just to a slide to just point out that Painlevé transcendent, they will appear in this talk in terms of non-relativistic quantum system with higher order symmetries, but they have appeared in statistical mechanics, quantum field theory, symmetry reduction of various equations. And here, this is just, let's say, one places where they appear. So this is why they are so important for mathematical physics. Okay, so one place where you can find Painlevé is not in context of, let's say, super integrability or even integrability. We are in context of one dimensional system, and we can be looking at different case of, let's say, algebraic model, either with operator L, which commute, give you back the, let's say, identity, give you back the Hamiltonian, and give you back that operator. So you could characterize those different cases as abelian, Heisenberg, conformal, or ladder. And I will point out that if you look carefully at the classification of those quantum system, you will find Painlevé. So this is, and there is a connection also with time-dependent integral as well, and also time independent as well. You can construct multidimensional system based on those building blocks, let's say. Okay, so here this is just a slide to say, as usual, people have not been the first one to study something, so there is scattered in different work some example. In what I will mention, there is more, let's say, in-depth classification based on Schelze equation, and also more recently work by Cosgrove, where third, fourth, and fifth order equation have been, with the Painlevé property, have been classified. Okay, so just as to illustrate, if you have a fourth order ladder operator, you can find explicitly a potential that depend on Painlevé 5 and its derivative. And here I don't give you the formula for F1 and F0, but they depend on higher derivative of V. So in some way, this is quite complicated object, but this potential admit, as I said, operator L, which is a ladder operator. But in some way, if you take the adjoint, you will be able to define not only the lowering or raising, but both of them. And you can begin to look carefully at their zero modes. And it looks like what I present below. You see that this is something that depends on Painlevé 5 and its derivative. It has a specific structure. Both ladder operator have four zero mode, meaning that both the raising and lowering operator annihilate possibly four states. One need to look carefully at the asymptotic of Painlevé 5 to be able to, in terms of the parameter, to be able to say what type of pattern do you get? Do you get infinite sequence of level, or do you get even finite sequence? So you can, that has not been completed for this Painlevé 5 case, but it has been completed for some Painlevé 4 case. Okay, so this is just one example, but you see that this is quite complicated, and we go very far away from this Lamé operator and potential in terms of elliptic function. And if you just look at those four cases more carefully, you then get hierarchy of quantum system, and they have properties. For some have been revealed, for some have not been revealed at all. Okay, so here just to connect with some talk yesterday and some talk that will be also on today's schedule. Integrability, superintegrability. That is defined when you go in higher dimension than one, so at least two. So in that context, you can speak about integral of motion from the side of Poisson bracket in classical mechanics. So they are integral that are polynomial in the momenta. The Poisson commute with the Hamiltonian with each other. So this would be integrability. So if you have n of them, if you have more, then this is super integrable. There is then a lot of properties to those systems, in particular the maximally super integrable ones. And this extends to quantum mechanics with some effort because you need to then have well-defined quantum mechanical operator and they need to form algebraically independent set. Okay, so this will be the context that I will discuss. And as said, there would be connection with Painlevé transcendent. Okay, so what is the context of this problem? It goes back to even the 60s. So you select your Hamiltonian, you look for a specific type of, let's say, interaction, or is it scalar potential? Is it a magnetic field? Is it with spin? Is it with position mass dependent system or on curve space? Here I am on Euclidean space, two-dimensional Euclidean space, and I'm looking for integral of motion that are polynomial. So then if I ask to have one such integral of motion, it connects with separation of variable in Cartesian polar elliptic parabolic. But if I ask for two integral of motion, which is then maximally super integrable, I will then get a list of four potential. This is one example. We can see that it extends the Kepler-Coulomb interaction with some potential that depend on the angle, which is interesting from, let's say, modelization point of view. It connects, for example, with benzene molecule. And this is something that is a general feature of those super integrable system with quadratic integral. But what we want is to look for higher order integral of motion, so those higher order symmetries. So this means that one need to look for operator X that have dependence as cubic, quartic, or kinetic polynomial in terms of the momenta. Okay, but this is become more difficult to make the classification. So just to say one word about those quadratically super integrable, just to motivate some of their properties when you go to higher order integral. They have been classified on conformally flat space in two dimensions. They connect with quadratic algebras, they connect with orthogonal polynomial, and there is some work, for example, by Douglas, Junza done on model on Darboux spaces. Those are quite interesting because they have non-constant curvature and their spectrum are quite complicated. So then it makes it interesting to look from side of representation theory. So there's still an ongoing, let's say, story, even for quadratically super integrable system. But what we want to discuss today is when you go to higher symmetries. So this is what higher symmetry would look like. So this is something that is a polynomial in terms of the momenta. This is in two dimensions. If you look for, let's say, what I would call n equal 3, so third order integral of motion, you can restrict to the odd term because the odd and even term, they commute separately if your Hamiltonian is Hermitian, and then this is the compatibility equation. So what I wanted to point out about the compatibility equation is we can see that the fourth equation depends on h bar and the leading derivative term. And this point out that one cannot classify superintegrable system by simply going to the classical setting with Poisson and then quantizing. You need, in this context, to get some non-trivial interaction, look at the quantum deformation, and the system, they won't be in one-to-one correspondence. They will be different problem. So as this is pointed out in the literature, very often model like Calogero, harmonic type of oscillator, deformation of Kepler-Coulomb, they are more or less they're in the type that they are quantum and classical. Okay, so they have the same quantum analog, and then of course they are interesting to study, but then they are in a very particular type. Those one here would be the purely quantum system. So if you do that process of classifying system with a second order and third order integral, and you restrict to a particular type with separation of variable, you get on a list which depend on Painlevé transcendent, and those actually are quite interesting. There is some properties for the fifth one, the one in terms of Painlevé 4. It allow third order ladder operator, which allowed then zero mode. So both the raising and the lowering operator have three up to three zero modes, and then you have the possibility of having different, let's say, pattern for the level, infinite sequence, finite sequence, and there is some open problem that were solved recently, as it was conjectured that only singlet and doublet were possible, but in fact, multiplet are possible. And then maybe this is some also other open problem for PhD student or postdoc. Uh, those four models with Painlevé 1 and Painlevé 2, no one have ideas what their wave function may looks like, their spectrum. No information have been obtained so far, so this is completely open. And if you look in some way, they generalize again this Lamé operator in some non-trivial way. So probably they have some properties that are not trivial to look at. Okay, so here I just want to, and I won't go on further with the classification because it gets, let's say, more complicated as you increase the order. But just to convince everyone that there would be pain levé along the way as you increase this degree of the integral. But here I'm restricting to very specific case of second and fourth order. So this is not even a complete classification of all system with second and fourth order integral in two-dimensional Euclidean space. So this is very restrictive. There is 12 model that one obtained. And again, this is the some compatibility equation below on this slide. And there is some other compatibility equation for those unknown function L of x uh, and Ly. And then there is one compatibility equation for the potential. It is linear at this point, but if you want to classify everything, you will get equations which are nonlinear, and then this is where it gets complicated. I won't get into the, let's say, the process, but I will give you some detail about the classification. You will then get, so all those models have a second and a fourth order integral, and they will depend on first, second, third, fourth, and fifth pain levé. So you can see that this is, again, quite complicated, but all those potential then need to enter into a Schrödinger equation. And this is a PDE, which depend on the potential that depend on rational function of pain levé and their derivative. But still, some of them have very nice property, but this model, for example, with Painlevé 3 has not been studied at all. So still something that is an open problem to be looked at. Just a few words about the classification. At the level of third and fourth order integral, you will get third or fourth order compatibility equation. You can integrate the fourth order one, and you can manage to connect with the Chassis equation. So this is the form. Again, I won't go in terms of more details, but you need to have some assumption that the parameter algebraic number, that function are analytic in Y, and there is other assumption, but there is 13 classes, and the first type, which is called Chassis 1, has the following form with some dot dot dot, and you can integrate this one in terms of what is called a second order, degree ultimately pain levé. But here this is just some detail on this, and some connection also with what Bureau has done in the 60s. So you need to look at not only the Chassis equation, the Chassis 1 equation, but you then need to look at what happened when you manage to integrate this equation. And ultimately, the form will be related to the work of Cosgrove and Skoufis, which is the second order and second degree, they have looked explicitly at all the reduction to pain levé transcendent. Because the idea is that once you get this equation of higher order, you manage to get the Chassis equation, you manage to get a second order, second degree pain levé, you would then need to look at transformation that allow to bring that equation to a pain levé equation. And if you manage to do so, you can then manage to obtain the potential explicitly in terms of a function of pain levé and its derivative. Okay, I won't give any details, but something that has been applied and it worked for super integrable system with third, fourth, fifth order. But there is some cases that do not have reduction to pain levé transcendent. So there is even a beyond in some sense, but still with the pain levé property. Okay, just one example to convince us that there is interesting property. This is a Hamiltonian here that the potential break down in two pieces. Something that depend on the radial variable, so looks like isotropic harmonic oscillator. And there is some singular term that then depend on this function t, that is a function of the angle. And this Hamiltonian with the following potential as a second and a fourth order integral. This is the form of the fourth order, but here I give it in terms of the Cartesian coordinate. And if you manage to solve the compatibility equation, along the way, you will get one compatibility equation for this function t. Okay, so this is second, in fact, fifth order, so it depends on T5, but you can integrate this one time, two time, you get then a Chassis equation, you can then integrate, but you need a integrating factor that is correct, you need also appropriate transformation, and along the way you get a second order, second degree pain levé, which admit a reduction to pain levé 6. Okay, so this equation above, there is a transformation from W, which is rational in pain levé 6 and the derivative, which allow to convert in terms of pain levé 6. So you can obtain explicitly T in terms of a complicated expression of pain levé 6 and its derivative. And that has been done, and there is some further work because this is still open to understand completely the underlying symmetry algebra. But here, let me just present some detail on one specific case, because the pain levé 6 or its Chassis, let's say, form above, depend on four parameters. And those four parameters, they have a special rational solution for specific values. And for one of it here, I won't give the detail. You need to take Q7 up to Q10 as a quartic expression of some parameter and alpha and beta. Here you see that the function t reduces to some trigonometric expression. But along the way, if you make carefully your way back to the potential via the function w, there is a connection also with exceptional orthogonal polynomial, which I won't point out. You will get the following Hamiltonian. So in some way, when you look at those models that involve pain levé transcendent, you should not just see them as something which depend on higher transcendental functions, but something that encompass in some way infinitely many model which has rational interaction or depend on hypergeometric functions. And here, this is just one example with its corresponding integral of second order and fourth order. I'm not giving anything explicitly. We can see the function g of xy. And again, this is in the xy coordinate. I don't give you in terms of the coordinate r and phi. It would be even more complicated. But if you do this carefully in terms of symbolic computation software like Mathematica, you then can show that it satisfies cubic algebra you can obtain the structure constant explicitly, and you can then manage to even obtain Casimir invariant, connect with the between the Casimir invariant and the Hamiltonian. You can apply deform oscillator algebra method to then obtain finite dimensional representation, because if you can find a finite dimensional representation for this deform oscillator algebra, you can then carry that over for the algebra, which is cubic. And then you can obtain the spectrum via some constraint on this function phi. So I won't give more detail, but this is just to illustrate for a PhD student and also young postdoctoral researcher that then this is something that is useful to get insight into those models, but also from a purely algebraic manner. Because what is the point in some way to find integral of motion or higher symmetries, if not to be able to facilitate obtaining the solution in some ways? So this is one example where you can use this complicated integral to solve the Hamiltonian, meaning obtaining the spectrum purely based on algebraic manipulation, not solving the even underlying uh, Schrödinger equation. Okay, so just some open problem. I know this was a overview of those higher system with higher order symmetries, connection with Pain-Levé. This is via the Chazy equation. Just to say that you can extend that to curved spaces, hyperbolic space, the sphere. This is, again, two-dimensional space. Nothing is known beyond two dimension. There is some trick where you could find model with arbitrary number of dimension with Pain-Levé 4 and 5 and show that they are super integrable, but there's no classification beyond uh, what I mentioned. There is some also question about solvability, as some of those models have been let's say, solved via their ladder operator zero mode. You can only obtain the wave function for the excited state via an iterative approach, meaning you can only act on the zero mode with the raising operator, but then you don't have any explicit formula for the wave function. So this goes beyond any usual definition of exact solvability. So then where this fit into a mathematical definition of solvability. There is also some special case where the Pain-Levé admit rational solution. They have a very interesting property. Just the case of Pain-Levé 4, it connect with those generalized Hermite and Okamoto, and you can show explicitly that the pattern for the spectrum can take different form. It can be infinite sequences, one, two, or three, one infinite sequences with a doublet, or even a multiplet. So this is quite different than what people encounter for usual super integrable system where there is just, let's say, one sequence of level. Also, there is still a lot of unknown for a model with Pain-Levé 5, Pain-Levé 6. What is in some way blocking the way of understanding completely those models is question of asymptotic special solution. There is some recent work in 2024, 25 on special solution of Pain-Levé 5. There is some belief that the asymptotic is known, but for Pain-Levé 6, this is still also largely unknown. So then what would be the quantum analog of those model when you look at the special point where there is rational solution? This will then be open. And as I mentioned, there is no understanding of the model with Pain-Levé 1, 2, and 3. Okay, so in some way, this is something that is exciting, but there is some open problem. So then there is a lot more to say. And just to point out that our original, let's say, non-trivial model that I mentioned, the one related to the Lamé operator in terms of elliptic function, has found its way to so many areas, and there is still some, let's say, properties that are revealed every year. I believe that those model with Pain-Levé transcendent probably would have a lot of properties to be revealed as well. Okay, so this is a first part where everything has been done with, let's say, differential operators. And I just want to take the opportunity to also connect with other talks that have been uh, either yesterday or will be this afternoon or tomorrow. For example, Anthony will discuss on further property of the classification. He also makes some progress on ladder operator connecting with PNLV6. Also, this question of quasi-exact solvability that CU will discuss. Is there any QS system that are in terms of PNLV transcendent? This is also some open problem. Yesterday we mentioned about Calogero. Is one could think about making many body Calogero interaction by finally, let's say, selecting the potential. This is something that is also unknown. Again, I just want to point out that many or most of the model in the literature, they are starting from the classical or the Poisson setting, and then there is some quantization that is happening. In some way, what I mentioned with the third order case is that the compatibility equation for the higher order integral depend for the leading order term in terms of h bar. So you need to proceed to the classification in the quantum setting if you want to obtain those purely quantum system. If not, you will miss out a lot of model that may be interesting. Okay, so just some further ideas for PhD student. Yesterday there was some work on geometric setting, and there was also some work related to Poisson algebras. What I want to mention is that an alternative or complementary point of view to the classification of superintegrable system, in particular with higher order integral, is to forget about realizations and explicit underlying space or in geometries, but to work with Lie algebras and then look if Hamiltonian integral and different properties can be completely defined via polynomial in the enveloping algebra of Lie algebra. So this is a completely distinct approach. There is some overlap, but to some extent there is also probably differences, and I will point out some differences just now. Here, this is just some references. Those references are to where the idea of this, let's say, algebraic setting originate. I will point out some work where there is more, let's say, defined classification and search for those algebraic superintegrable system with higher degree integral. Okay, so here just one very simple example. This is a two-dimensional singular theater. It depends on two parameters, A and B. So this is, of course, well known. It can be solved in terms of Laguerre polynomial. It admits also various generalization. You can look at self-adjoint extension and so on. But if we make, let's say, this transformation, you can write it in, let's say, what I would call an algebraic form or standard form, where only polynomial appear for your variable. And this also applies to the two integral of motion x1 and x2. So here I have a Hamiltonian h, where I have second order integral, and they commute with my Hamiltonian h, so as differential operator under the Lie bracket. They satisfy a quadratic algebra. So then we could think that everything is understood. Not only I have my Hamiltonian, I have my integral, they commute under the commutator as a quadratic algebra, can look at the representation, the special function. But let me play a small game. Let's look at the, let's say, underlying Eden algebra. So this is from the side of GL3. So let's say someone give you those operators G1 up to then G8 and X and says, let's write those integral of motion x1, x2, and this Hamiltonian h in terms of those operators. So a priori, we could wonder if this is possible. This is the explicit commutation relation. They are not overly important for what I will mention, I mean the explicit form, but we just keep in mind that you can write those commutation relation in the following way. and that you can manage to write not only the Hamiltonian, but the integral of motion in terms of those operator G1 up to G8, and then X is a constant. So then, of course, you can manage to also use this operator. But the point is that this operator X1 tilde, which is in the algebraic form, do commute with the Hamiltonian under the Lie bracket of the algebra GL3, but not x2 tilde. So in some way, the integral x2 tilde, even if it is formally the same, okay, than the one I started with here in the differential operator form, in fact, is not at all commuting with the Hamiltonian in the algebraic form. So it means that there is a distinction between the enveloping algebra of differential operators and the enveloping algebra of the algebras. So in some way, there is two different settings, the differential operator setting and the algebraic setting. And in some way, you need to wonder which one you want to apply, and there is different reason to look at one or the other. You can then begin to play a game which is finding polynomial in the enveloping algebra of GL3 such that it commute with the Hamiltonian H hat, which is in algebraic form. And you will find that, in fact, there exist several polynomial and they are no longer of second order. In fact, you will get many operator of third order and they will satisfy complicated relations. So here I'm just giving you some of those relations. So in some way, the quadratic superintegrability, so the fact that you have second order differential operator that commute with the Hamiltonian is just an artifact of a choice of realization for some algebraic setting. So if you look at the algebraic setting, necessarily you are obtaining higher degree integral. And then the question is how many? And then is this number the same as the setting when you use explicit differential operator? And in some way, those are not the same. Okay, so what I would like to advertise now, and this has connection with talk yesterday on Poisson algebras and in some way centralizer algebra. This is the notion of commutant. So you forget in some way this explicit example with the singular oscillator, but you then wonder, let's start the problem over with semi-simple algebras and think about what would be an appropriate subalgebra to find polynomial which commute with the subalgebra. And this would be, for example, the Cartan subalgebra. This is something that is ongoing also with Junzi Zhang and other collaborators. So we are looking at how to extend those approaches. Here I would just give some detail, not everything. So this is a definition of a commutant. You have a Lie algebra G, you have a subalgebra G prime, and then you look for polynomial, not differential operator, that are written in the enveloping algebra of G, which commute with all element in G prime, and those G prime invariant polynomial then will be part of the commutant. Computation of this can be facilitated via symbolic computation software. You can begin to classify all those polynomials, the indecomposable ones, so the one that do not depend, let's say, on the lower degree one. And you can also begin to think about is there is another setting which allow to get similar information, but in a simpler way. And this is the Poisson-Lie bracket and a variable of the dual space. As I said in the first part of the talk, if you proceed with differential operators or explicit realization, you need to be careful because there is a difference between quantum and a classical setting. But here we are doing the opposite. We are trying to get insight into this commutator setting by going back to some Poisson analog, and then there will be a, let's say, a process of quantization in between both. Okay, so For the variable of the dual space, you then have a Poisson bracket, which is defined as follow with the structure constant. Then you have the possibility of finding Poisson bracket for any function or polynomial of those elements of the dual space. You can then find a criteria for the commutant or centralizer subalgebra in context of the symmetric algebra. And the map that goes back and forth this Poisson setting and this commutator setting is the symmetrization map. So in some way, this is something that can be, complicated to do in practice, but can, of course, be done for specific cases using symbolic computation software. Here, this is just to highlight that you can then proceed to a search for the element of the commutant via PDEs, because in the Poisson setting, the criteria for something to belong to this commutant reduced to a set of PDEs, and then it can be solved either directly by assuming that this is polynomial or by solving the PDEs via, for example, method of characteristic or other approaches. Here, this is just a final slide, let's say, on the, let's say, more mathematical framework to say that one can understand that those polynomials of the commutant, they will close both in terms of the Poisson setting for the dual space and the symmetric algebra, or in terms of the commutator, when you go back to the Lie algebra via the symmetrization map. This is because in some way you will exhaust all the indecomposable polynomial when you go to a certain degree, okay? But in practice, the degree at which you need to stop may be quite high, in particular if the rank of the underlying Lie algebra is also large. Okay, just some ideas here about this other type of classification with higher order degree integral, but in the algebraic setting. So this is something that is ongoing. So that has been looked so far for AN, BN, CN, DN, also mainly Zhongze have been making progress into various proof for this, and also complete classification have been done on for the conformal algebra and connection also with some super integrable system on those Darboux spaces. Okay, so this is something that is ongoing, but in that setting, your Hamiltonian, your integral, your let's say polynomial algebra, they are completely algebraic and understood in some way via some underlying Lie algebra. Here, this is just a small game for the AN case. So the commutation relation are well known. It is well known how to go to the dual space. The form of the polynomial a priori are well known, but what we are interested in, as I said, is the indecomposable one. So the one that cannot be written in terms of lower degree. So then one need to spend some time to count and to obtain relations among those polynomial, and then that can be quite difficult in practice. But for AN, it can be done. Here, I would just give you one example related to SL3. Those P12, P13, P23, P123, they are given by polynomial of the following form. Okay, so this is just a product of the element of the Lie algebra, and this Poisson bracket is made out of the Poisson bracket from the dual space of SL3, and it closes in the following way. Okay, so this is one way to think about this model, and the Hamiltonian will be formed by the Casimir and some combination of the Cartan generator. Then you can perform various, let's say, trick to rewrite that algebra. One of it involves the Casimir invariant. So here I would just give some detail on those change of variables. It will go two ways. One is to use those integral f1 to 3, g1 to 3, which have some nice symmetric and anti-symmetric properties. And it allows even to do something which is I had the algebra which was defined for P12, P23, P13, P123, and so on. Now I can do something which is defining an algebraic structure which is valid for all, let's say, IGK, which take value in 1, 2, 3. So in some way, all the choice of indices are then allowed. So then you can connect with some other algebraic structure in this approach. So this is the explicit Poisson bracket, the constraint. So I want to say, let's say two more things on that example, which is if you perform change of, let's say, basis made with the Casimir invariant, because we know that SL3 has a second and third order Casimir, you then can rewrite. And if we look carefully at this algebra here with structure constant, which depend on certain expression on the Cartan generator, the second order Casimir, the third order Casimir, you can then write in this compact form. And if we go back to the beginning when I was talking about quadratic superintegrability and Racah algebras, this is a Racah algebra. So now we have found some algebraic structure which would have been coming from this classification using differential operator, but in an algebraic setting. Another thing I want to point out for that example is quantization. I said that quantization can be made by applying the symmetrization map. I just want to do it explicitly here for SL3. Just one comment for SL4. You will then get a larger structure, and this can be done also explicitly. But for this SL3, you see that this is no longer homogeneous polynomial. You see that there is some lower degree term, which appear to be trivial in some way for that example, but this will have the effect to change your commutation relation. Here it means symmetrization of this expression in terms of the algebraic integral, and those are the deformation terms. And the same also follow for this. So in some way, you can proceed with a complete description in the quantum case. And this has integral not only of second order, so for example, Cig or Cik, but those one or third order integral, the f and the g, because they have three indices. So in some way, this is another approach to get access to higher order integral but via underlying Lie algebras. Okay, so just a comment over the whole hierarchy of AN. This can be done. It grows very fast, and up to SL7, you will get algebraic structure with thousands of elements. So then there is a question of what is the best way to present those system, their integral of motion, and you get at some point a large number of polynomial. So then it questions even what integrability and superintegrability mean in that setting, but you can still bring back a geometric setting and realization. So this is something that is also being done, and you can define a superintegrable system via those geometric approach. Okay, in the remaining 2 minutes, I just want to point out, couple of overall comment. One is that we mention often integrability or superintegrability, but in some ways, those have a connection with other topic. Subalgebra, chain, dynamical symmetries have been looked in context of nuclear physics for a long time. And to some extent, they have a similarity with this problem of integrability or even superintegrability, the question of missing labels. So in some way, when we speak about integrability or superintegrability, we want to encompass maybe a larger class of problem, which are formally speaking similar. And this is something that is being done also for different subalgebra chains. So to some extent, we might want to think about integrability and superintegrability as one particular setting, which is taking different aspects. Okay. Last slide. So this is just to connect for this second part on the algebraic setting with other talk. So just to say that, of course, you can bring back in this game different geometric setting, but it is not trivial, and this is something that is ongoing. You can also play other games with Lie algebra, Q-algebras, co-algebras. You can work also with not underlying algebra, which is a Lie Poisson or Lie algebra, but something else, sometime quadratic algebra. So this is something that Peter and Victor and also Samuel have been working and will speak later on. There is also other approaches to integrability and superintegrability than the one I mentioned. So this is also something that other talk will mention. So then this would be the end of my talk. Thank you for your listening.
Okay, okay. Many thanks. Thanks for Ian for his talk. So, any questions, particular questions for the speaker? Okay, so I actually have some questions about the Pahlavi equations. So, I mean, if you just go back to the pages where you define those equations, so
Oh,
because
yes.
those kind of equations, I was taught it's actually linked to another like indicable system, which is called a discrete indicable system. So, is there any like connection from Liouville inequalities and to those discrete inequal system?
Actually, this is an open